Good morning, everybody. This is the SIG Multicluster Deep Dive. My name is Paul. I work on the Kubernetes ecosystem at Red Hat, and this is my esteemed colleague, Irfan, who works for Huawei. So today's agenda, we're going to cover just really quickly the mission of this SIG, talk about the different sub-projects, and excuse me, then do a deep dive focusing on different aspects of Federation v2. So the SIG Multicluster Mission, and I'm glad you're all sitting down for this shocking news, is to solve common challenges related to management of multiple Kubernetes clusters and the applications that we want to deploy on them. So that includes designing, discussing, implementing, and maintaining APIs, tools, and documentation related to multi-cluster. It doesn't necessarily include only particular styles of approaches like the one that we take currently in Federation, and also includes standalone building blocks, and if there are changes to push into Kubernetes where appropriate, includes those too. You can read more in the SIG Multicluster README at the link below.
So some of this portion is already covered as part of intro, so we are just quickly gonna browse through them. So we have 3 active projects right now. Federation v2, what we call, is the most active of all of them. We also have cluster registry and kubemci. The details of that has already been covered in intro. We are more interested in diving deep into Federation v2 project for this particular deep dive session. So what we did not cover as part of intro was something about the history of Federation, or there was something called Federation v1, or when it was designed, it actually had some original goals. We still stick to those goals, and those are mainly to do with problems associated with handling multiple clusters. So when you have, or why the users would need multiple clusters. So if a single cluster is running out of capacity, that is when a user wants another cluster or more clusters. When there are workloads which can be run which can be run in one cluster but cannot be run in another cluster, which are, say, security sensitive, or because of some policies they need to be run in some geography alone. That is also a reason to have multiple clusters. When users want to avoid being stuck to a single vendor, that is also when there's a possibility for users to use multiple clusters. And HA is obviously one of the main reasons to have more than one clusters in case a single cluster network connectivity or the whole cluster goes down in itself.
So you've heard us talk about Federation as being v2. We're going to talk a lot about Federation v2 today. But one thing that we want to mention is one of the main motivations for v2 is that we have a very different world today than when the original Federation project was created. The most salient difference is that now Kubernetes has an API surface that can be extended by Kubernetes APIs. So you may have heard of this thing called custom resource definitions, and that really means that in order for something like Federation to be useful, it has to support types that we don't know about in advance when we write Federation. That has motivated us in Federation v2 to move to a purely configuration-driven approach and base Federation v2 entirely on CRDs. So just to go over some of the use cases that we support today, the headline here is that you can add Federation support for any Kubernetes resource, whether it's in an API server, maybe the Kubernetes API server, or one that you wrote yourself, or a custom resource definition. You can deploy workloads composed of these arbitrary API resources across multiple clusters with an active push reconciler, meaning that we're pushing API resources from where Federation is hosted into the target clusters, and customize different fields about these resources per cluster. So this is kind of like the basic level of workload distribution. We have some really interesting behaviors built on top of that for cross-cluster service discovery. It's a little bit of a tongue twister. And service failover across clusters, and then also dynamic rescheduling and rebalancing of replica workloads across clusters. But those are really just 2 examples because the sky's the limit, and we'll talk about how you may want to write your own higher level controller or operator that targets federation. So one last thing for folks that are interested in how do you actually run this stuff in a cluster. One of the most interesting things to me that we've done in Federation so far is that you can deploy Federation on a namespace basis, meaning that you can host multiple copies of Federation within the same cluster. You can have different users target the same cluster and not stomp all over one another, so to speak. So who's ready to jump off the diving board? I've got my swim trunks on under here, but you're not going to see them today. You may have seen this, this diagram if you read the blog post that we published onto the Kubernetes blog, and may have seen this in the SIG intro, but Irfan and I made this diagram, so we felt like we could use it again. I do notice, looking at this, that it's an awful lot of boxes. So perhaps, Irfan, maybe we can just constrain this to something smaller, more manageable to start with.
Let's zoom in. So I've restricted the whole diagram to, say, 6 boxes right now. And let me explain what these are. So we have, in the blue big rectangle that you see, we have a template. I hope it's legible. We have a template, a placement, and an override. Those are basically type definitions of the APIs that we associate with a target resource in a given K8s cluster. So this is basically all the information that is provided additionally for federating a resource in the federation control plane. Then we have other 3 are the type configuration and propagation. That is inbuilt or the core type definition of provided inside the federation control plane, which specifies the association between the target type and the type definitions that I specified as template, placement, and override. And then there is cluster configuration. That is also one of the core resources within the federation control plane. So how exactly the control plane knows about what clusters to propagate to? That happens, or that can be done using kubefed join. So when a user does, or an admin does, a kubefed join, he basically is specifying a target cluster and telling the control plane that this is one of the clusters which will be associated with the federation. And multiple clusters can be joined to federation. And we haven't put any limit to that also as of yet. How does federation know, or the control plane knows, what type to associate with? So we have provided a tooling for that also, that we call it kubefed federate. And what it basically does is creates the type configuration associating a target type and the type definitions which are there in federation control plane. Once these 2 things are created, we have a sync controller or a sync loop, which basically can propagate the resources based on the specifications in the template, placement, and override to the target clusters, and create or reconcile resources over there.
So when we were planning this presentation out, we said we can't have something that's a deep dive session without showing YAML. So we're going to see some YAML now, some examples.
Cool. So we talked about the type configuration. This is just a concise YAML representation. It's not the whole YAML also, of what a type configuration looks like. So what you see here is you can find on the 7th line, you find the target. So this basically is specifying that the target resource for federating the resource is the deployment here, and the version can also be specified, which is v1. It also says to associate this target resource with the definition in federation control plane, the template, override, and placement types are what. So the federated, or the names of those types are what. So the federated deployment is the name of that type, of the template type. Federated deployment override is the override type, and federated deployment placement is the placement type. One of the very key information also, which is the last line and specified in blue, is the propagation enabled. So this tells the controller or the sync loop to propagate the resource or reconcile the resource in individual clusters or not. So this is a totally admin defined stuff, or this is the configuration provided to the admin, of which can be created and controlled by the admin. Next, on this slide, we have put the definition or the CRD definition, which will define the type of template. So this is defining the API type in Federation. So we don't have any code so far written for that. Additional code that we have to bootstrap the API and all that stuff, it is not needed at all. We just create the CRD type and install it on a given Kubernetes API server, and that's the associated template type. Same way we have the associated placement types and the override types. We have just removed the YAMLs for that because it'll be too much of YAMLs otherwise. Now let's have a look at the actual object or the actual resource. So we have a type definition already there, and if you look at this resource YAML, what it is specifying is it is the kind federated deployment, which we have called template, and the spec is nothing but actual deployment resource in a given Kubernetes API server. So whatever deployment resource that you want to propagate to the individual clusters, that is what you would specify over here. In the placement, there's nothing else but the list of clusters. So the spec basically defines that as the list of clusters. That's the list of clusters. Among the federated clusters, this resource should be federated to. And we have been able to implement a generic override mechanism also, where you can just specify a cluster, a path, and a value which needs to be overridden in that cluster at that specific path in the spec of the given resource. So I think we have some understanding of this. Go ahead.
We bungled the transition there.
No issues.
It's all right. I hear you get one before they kick you out of KubeCon, so we're okay. So now we understand a little bit more about this big picture with a lot of boxes, but there's some that we haven't touched on yet. I want to draw your attention down here to this box status. And sort of equally important to spec, you could say, in Kubernetes APIs. This refers to, though we have talked a lot about how do we get resources into clusters that we're targeting, we also want to understand what the status of those resources are. Status is one of the things that can be an input along with policy, which might refer to something like data jurisdiction requirements that say that a particular workload has to run in a particular geographic boundary. Those two things, status and policy, are inputs to the concept of scheduling, which is moving workloads around, scaling workloads, et cetera. And scheduling is an example of one of these higher level APIs that we want to enable people to write and target the lower level Federation primitives. Another one is the DNS feature of Federation, which allows you to program DNS records for federated services and ingress. To do the DNS provider programming, we're using a project from another part of the Kube ecosystem called external DNS. And what this allows us to do is to get exposure to a large number of DNS providers without actually having to become experts in programming DNS. So now that we kind of understand the lay of the land, since this is a deep dive, we're going to zoom back in on this box propagation there and talk about exactly what happens to make all this stuff work. So one of the themes that we're going to have presented a number of times in this slide is that the same process happens whether we're talking about a built-in Kubernetes API type or a CRD that no one knows about but us. Our SIG-Multicluster Deep Dive 2018 North America CRD. So obviously we've got a Federation API surface, right? And we've talked about the federated type config resource that Irfan has just walked us through. The type config controller is watching the federated type config resource. And when, for example, we see one that points Federation at secrets, as an example, the type config controller starts a new sync controller for the secret type. And that handles, doing the math basically of figuring out exactly which state of the secret goes to which cluster. And then since we're using push propagation right now, actively pushing the secret resources to the right target clusters. Similarly, if the type config controller sees a new federated type config for the service type, It's going to start a sync controller for services. And that's going to do the exact same thing. Do the math, figure out where stuff is going to go, push it there, et cetera. Now, this is made possible using the same code path by the dynamic client and unstructured resources, which mean that we don't have to differentiate the control or differentiate the code for these different resources. It's the exact same code that runs, which is pretty neat. I'm glad that we have smarter people than myself working on this API machinery and client Go stuff to make all this happen. So that's how we turn it on. When we want to turn it off, oh, sorry. Well, I kind of talked through this. There's some boxes here that represent all the other things you might want to use this on. Same stuff runs for those. So when we want to stop propagation of resources, we can delete the federated type config, or you can flip that propagation enabled bit that we saw earlier. And what happens at this point is that the type config controller gets a watch event, says, hey, I need to stop the propagation for this, and it will stop these controllers that it started. You want to talk about scheduling?
So the code or the code base for schedulers is also very similar to the sync controller. So there's an API surface, and there's a scheduler manager that we call watching similar type config for the target types. For example, we have written a scheduling controller for deployments. So for deployment type, the scheduler manager watches the API surface, and if there is a type config that is created by an admin and a type definition already provided for deployments, then it basically starts the scheduling controller, associated scheduling controller for deployments. The same way, so this is also to provide a reference mechanism for any high-level controllers to be written and implemented in a very similar fashion. And the implementation of these controllers is such that a new, say, scheduling controller can be plugged in very efficiently without updating much of the code. So same way, when a type config or the target type is removed, the scheduling manager understands that it has been removed, and it will just stop the scheduling controller for that particular type, for example, deployments.
So we've thrown a lot of API resources at everybody today, and to keep them straight, we put them into different groups. The federated type config and federated cluster resources are part of the intrinsic API for Federation that programs Federation. Those are in the core group. The primitives group contains the auto-generated resources for the Federation APIs, and scheduling and multi-cluster DNS groups scheduling group and multi-cluster DNS groups are pretty much what they sound like. They hold resources for the scheduling and DNS APIs. So since we do have a lot of different API pieces that work together, we needed a way to have an API that wasn't riddled with object references. In order to do that, we have come up with a naming scheme that allows us to have a naming convention to make it very clear which resources in the Federation APIs align with one another. So as an example, if I've got a deployment called mydep, the template definition for that thing lives in the federated deployment, and the placement and overrides live in the resources of the same name and namespace. Similar thing with scheduling and multi-cluster DNS for services and ingress. Now, we've said multiple times how we're not writing any code to do this. Well, we don't want to have to write all this YAML either. So what we've done to enable that is the kubefed2 federate type command. This creates the federated type config and generates the Federation APIs. We touched on, maybe glossed over it in this run through of the validation schema. We'll generate a validation schema for the Federation APIs based on what the API server reports for OpenAPI, or if it's a custom resource, just slurp that validation schema up and reuse it in the Federation API. When we want to disable propagation or outright delete the Federation APIs from a cluster, we've got the kubefed2 disable and delete commands.
So the kubefed federate type was basically federating a type resource, or it tells the federation control plane to enable the federation for a given type, for example, deployments. But users still have, say, manifests or a whole set of YAMLs for their applications, which we think is also one of the reasons or one of the use cases where we can ease it for the users to translate those YAMLs into the federated equivalents. At least give the placeholders which are federated equivalents, and if there is some update needed, then users can go ahead and update those manifests. So we are basically working on that tooling right now. We are going to name it Federate Resource. So the Federate Resource, for example, deployment, can federate our existing K8s resource, which, as in this example, it says my deployment, or we can extend it further, and this particular tooling can take existing manifest as input and emit equivalent federated YAML for that same thing. We might also think of extending it as a plugin or some mechanism of extending the same thing into Helm-based implementations, because that's what we think might be the most used tool for deploying applications as of now. Okay, so last, what we are right now focusing on, or what is in pipeline or the future work for us, is usability. The highest on our list for now is usability. We have been able to build basics or the primitive basics properly, and it seems to work quite fine. So we are, like in the previous slide, we specified that we are trying to work on a tooling which will ease the translation of or transition of existing K8s resources into the federated equivalent. We also went through all the resources, and we saw that there are n number of set of resources. We are in the process of discussions of trying or figuring out if we should merge these resources, which might make it easy for the users. One of the very important things that we also want to take as a next step is the actual user-facing API. So because we have so many resources and there are so many different pieces that needs to be worked in together, it might make more sense to define API, which is a very concise presentation or representation of what a user wants to do while federating a resource. Status aggregation is also one of our goals for now. It's not completely done. We have some mechanism of consolidating the status from individual clusters, but we want to do it in a more tailored fashion where it might be something that user might be able to make meaning out of. We'll be working on more high-level scheduling behaviors, pull reconciliation, and then this list is not complete, it's not exhaustive, but these are the main pointers we wanted to showcase that we would be working on.
So before we do Q&A, I wanted to make a note that when we were discussing how this session should flow, we talked about doing a demo. We decided earlier today that nothing could top Dane's demo of deploying Istio with Federation that we gave in the intro session. So since we have limited time to cover all this material today, we encourage you to check that out if you'd like to see a demo. And now we've got some time for Q&A. Can we get a microphone for the questions? That'd be great. Why don't you ask your question, I'll just repeat it.
Yeah, I'm trying to pick one. You shared the command line tooling for Federation. Are there programmatic APIs as well? So as you add clusters programmatically, can you like add and remove them from Federation?
Absolutely, yeah. All the CLI tooling is doing is just making API calls. So for example, the kubefed federate enable command, it just automates what you would be able to do manually. It's just less annoying. Okay. Gotcha. All right. Maybe we can just ask questions and we'll repeat them. The question that I answered, which I forgot to repeat, is there an API surface other than the CLI commands? All right.
I played with Federation a little bit, and the namespace
So
I mean, I'm wrong, but that seems to be replicated automatically, and I wasn't sure of the control.
the question was that the federated namespace type has some different behaviors from the other ones. Irfan, you want to take that one?
So basically, all these API definitions that we are talking about, they are CRDs installed on a given K8s cluster. In that case, the namespace is used from that cluster. So when I actually install a CRD type, I'm actually installing that CRD type in a namespace in that K8s cluster. So there is actually no separate namespace which is federated. So you understand what I mean, right? So
I don't understand why I can't have a federated namespace in a non-federated.
So yeah, I mean, we have that also. So we have a namespace federation also. So where you can federate a namespace, but when we talk about the types definitions and all that, we are actually using a namespace from the K8s cluster on which the control plane is installed on.
So the question is about the matter that the question touches is the difference between a cluster scope deployment of federation and a namespace scope deployment of federation. So the difference being that in a cluster scoped deployment, the same federation controller has to handle multiple namespaces. In a namespace scope deployment, you're intrinsically bound to a single namespace that the federation is deployed into. Does that make sense? So the federated namespace semantics are different.
Slightly different than the rest of the resources.
Right.
You can say that.
We can take this question offline at the end. I tell you what, I'm going to just surf around here, and you can speak into the lapel, and you're closest to me here.
All right. So what's the production level, production readiness level of Federation? Is there anybody using this in production?
So that's a really good question. The API level is alpha right now. I think we had a slide where we talked about going to beta early next year.
We are expecting to go beta early next year.
In the meantime, we'd love to have any feedback if people want to kick the tires, or if you have the kindness in your heart and the resources in your calendar to do so, to try it out and give us some feedback that will allow us to make a good decision around that. All right, I see ya.
So you talked about So you talked about cluster level federation and a namespace scope. Can you actually do a group or set of namespaces or single federation?
Yes. So one of the slides we actually mentioned that the same cluster, a user can actually install multiple federations, and joining cluster can also be such that same cluster can be joining to multiple user-specified federations. So both of that is possible. Yeah, you had a question.
I'm asking,
There you go.
what are the use cases that drive federation?
Can you repeat that, please?
So what use cases require federation?
Oh, we covered that as part of our first slide. I mean, the initial slides, right? I think. So there were many set of use cases, and we also covered about the goals which might lead the user to consider federation. So which were like HA, or you don't want to be logged in into a single vendor, and those kind of things. You can probably go through the slides again.
So when you were talking about the scheduling, like where are there's custom schedulers for each federated resource type? Like where do those things come from?
So there is a possibility of custom schedulers for many types. For example, jobs could be scheduled, or all the types which have replicas basically, which are workload types. So we have done some reference implementation of the schedulers for, say, deployments and replica sets and jobs. And there could be more schedulers written to, have either a little different behavior than what we have implemented, or aggregate that behavior. And there are a lot of possibilities of that.
You've already implemented our deployments, replica sets,
And jobs, yes.
So we've only got about 5 minutes left in the session. I'll be around after if we need to take questions offline.
So as an app developer, what I would like to do is say, I want to deploy 100 instances in region US West. I don't care whether there are 3 clusters, 5 clusters, 10. I'm presuming this can be done with what you have. What would be nice is to explain how would an app developer express this concept without being able to specify clusters.
Yep. So what the user basically has to do is, as a user, you don't have to do that. The admin will basically create a federation. The use case could be solved in this way. That admin creates a federation, he has joined a set of clusters and he labeled the set of clusters as some US West and some are in US East or some are in Asia or someplace. And while creating the cluster, while creating the workload, the user specifies or labels the workload as that this workload should ideally go only in clusters which are US West, and Federation will take care of that. That's almost already in place. So there is something called label-based placements, which is under implementation right now and which will solve this use case.
Could you describe cross-cluster networking at a high level?
It's actually a complete talk in itself. So, and I actually attended a couple of DNS talks yesterday, and they talked about Federation and cross-cluster service discovery in Federation. So we actually did put out a blog yesterday, and some portions of that are covered in that blog. I encourage you to have a look at that. It's Kate's blog. Slides I'll be updating against the schedule.
You mentioned that there was a push mechanism to push the updates to other clusters. Is there any thing to decouple that so you can do like a store and forward in case you have an infrequently connected second cluster?
Paul, you want to answer that? You can.
Yeah, sure. Now, one thing that I'm not sure that we gave a great treatment of in this session is that the push reconciler that we have now is just one of many that we could have. In fact, like we're quite interested to have people implement alternate propagation mechanisms. Like for example, pull reconciliation is something that there's been some interest in the group so far. So certainly our intention is that people should be able to implement their own.
So it's a follow-up to her question, to the other question. Basically, without going in details, but will the goal to be one pod in one cluster be able to talk to the other pod in the other cluster through IP addresses? Will that be possible at all?
I can answer that. So the goal of cross-cluster service discovery is not enable pod-to-pod network. That is actually an overlay. The goal of cross-cluster service discovery is to be able for one application to talk to another application, not necessarily constrained by the boundaries of single clusters.
All right, we've got time for one last question here.
Yeah, I'm just wondering about the support of storage-related resources like PVCs and all that. Are they part of the federation as well?
I think Ivan, who is also part of our SIG, might want to answer that. He had a great presentation about something similar related to storage yesterday.
Federating your deployment around your storage PVCs.
So you understood the question, right?
Yeah, he's giving Ivan the mic up there.
You can just speak out.
So the way Federation handles actually enabling any resource type, in theory, it should work. So I encourage you to try it. There may be some gotchas with it, but persistent volume claims and storage-related resources should be enabled to be propagated. Does that answer your question?
Yeah, of course, there are all kinds of,
Right. So. Right. So yeah, the idea there is that you have the necessary resources in each cluster as you're propagating to those clusters. So you could one way you could do that is just using like the default storage class in each cluster, and then you can create PVCs and distribute them to different clusters, and then the default storage class can back that in each cluster.
All right, we are at time now. Thanks everybody for coming.
Thanks, guys.
We're around if you want to chat about this stuff afterward. Thank you.